So sometimes we're not able to actually go out and integrate a function. Sometimes the function is just we don't have any techniques that we can actually use in order to integrate it. Or in some cases, like for example, when we're using computers, we don't really actually want to utilize integration techniques because it might be too time consuming and because computers do calculation really easily, really well. So we might actually want some other way to do something what we might call numerical integration or approximate integration. If we have if we get a close enough approximation, it might as well be that we have actually found the value for the definite integral. Now we can't go out and find the values of functions, or we can't go out and find functions or the actual antiderivatives of functions utilizing these techniques, but we can actually go out and make really good approximations of the definite integral using the techniques that we'll go over inside of this lecture. So now we're going to look at 3.6. This is numerical integration. And what we want to start out with is we want to start out with that basic idea of integrating. So we've got a function, okay? And what I want to do in doing integration is I want to find, right, the area underneath this curve. Okay? When we first started learning about integration, what we did was we said, okay, well, let's break up this curve into, call it boxes, right? And we use something like a right sum or a left sum, depending on the Riemann sum, and it looks something like this, right? And we'd add up the area of each one of these boxes, and we'd get ourselves an approximation, so on and so on and so forth, okay? And that was the Riemann sum. And then we utilized this idea. We took the limit as n approaches infinity, right, for each one of these delta x's. We made these delta x's small, right? We made lots and lots and lots and lots of these intervals, and when we did that, what we ended up with is we ended up with the actual integral. Okay? So the whole idea here is the value of the definite integral is the area under the curve. And that is the basic idea that we're going to use when we do numerical integration or approximate integration. Is we're just going to get better ways of actually doing that approximation. The first technique that we're going to use is something called the midpoint rule. Okay? And so what will happen with the midpoint rule is, let's just imagine that we have a curve. If I imagine that I was going to do a right sum, or excuse me, a left sum, I'd go over and for each one of my intervals, my xi, say this is x1, x2, x3, x4, so on and so on and so forth, up until xn, until I have my n different intervals. What I do is, from my left-hand side, I figure out what f of, call it x naught, f of x0 is, and I'll multiply that then by delta x, and that gives me my area for the left sum. So we've got the left sum is going to equal, or each rectangle in the left sum will end up equaling f of xi, okay, times delta x. Now if I did the right sum, what I'm going to get is I'm going to go over here, and we could tell, let's actually choose a different one so we can really make it clear. Let's say I did the right sum for x3, okay? So now there's my right sum, and you can see in this case it a little overestimates, but my right sum is going to end up equaling f of xi plus 1. We're going to actually add 1, and then we'll multiply that by delta x, okay? Conversely, you might also see this one as written as f of xi minus 1 times delta x, and the right sum as f of xi. It just depends upon where you're starting your count. If you start at 0 or you start at 1. But those are your left sum and your right sum. Now the idea here behind the midpoint rule is, let's say for example I have x here, x4 here, and x5. Instead of choosing the right sum or choosing the left sum, okay, instead I'm going to choose the midpoint between x1 and x4 and x5. All right, so I'm going to choose the midpoint there to find f, my value for f. So this is going to be f of x4 plus x5 divided by 2. So basically it's going to be the midpoint of those 2 points, and then I'll evaluate it at my function x. All right, so my midpoint sum is going to have values of f of, and we'll write it like this, f of xi plus xi plus 1 divided by 2. All right, And what you'll see, like say for example in a lot of books, see it written as f of x I bar, where xi bar equals x1 or xi plus xi plus 1 divided by 2, or our xi minus 1 to xi. Whatever it is, all we're talking about really here is we're trying to figure out the midpoints between those two values, all right? And we'll evaluate f of x at that point. Now, in order to find my area, right, I'm going to then multiply that by delta x. So however big delta x is, that's going to end up being my area. And that's it. That's how I go out and find the midpoint sum. Then the idea here is I just add them up along whatever interval that I'm calculating for, and that gives me my approximation. So let's try one out. So let's write out our midpoint formula. And so I'm going to have a summation. Summation is going to go from I equals 1 up to n. Okay, so I equals 1 up to n, or I equals 1 up to n, and we'll use f of x I bar times delta x. All right, and then we're going to define that delta x, okay, is going to equal our interval, so b minus a divided by n, all right, and xi bar is going to equal xi minus 1 plus xi, all divided by 2. So it's going to end up being the midpoint of the two. So basically we're just going to create a bunch of rectangles, all right, and then utilize those rectangles in order to approximate the value for a particular integral. So let's utilize this rule. We're going to say, okay, let's take, for example, we want to find the integral. We want to approximate with n equals 5. So that's the number of intervals that I'm going to use. The integral from 1 to 2 of 1 over x dx. Now, we do know actually how to integrate 1 over x dx. That's not a problem, and then we can just substitute in for x. That'd be fine. What we want to do is we just want to kind of like, get a basic sense of what this thing is going to look like, okay? And how it is that we use numerical approximation. So I'm going to draw a picture. And so here's my 1 over x, right? Okay, and let's say, for example, here's 1. And what I'm going to do is I'm going to separate it out into five slots. So I have 1, and then it'll be 1.2, then 1.4, 1.6, 1.8, and then finally 2. Now, you don't obviously have to like write out the 1.2, the 1.4, 1.6, and 1.8. I'm just doing that for instructional purposes. Okay, so I'm going to imagine that I've got to draw my first rectangle, but I'm actually going to move up from, I'm going to be at 1.10, okay, because I want to utilize the midpoint. So I'm going to find whatever the value is for the function at 1.10. And so there's the function at 1.10. And so that's my first box. Okay, so I'm going to I'll find f of 1.1, and I'll multiply that then by, well, let's actually find delta x is going to equal 2 minus 1 divided by 5, and that equals 0.2. And that's actually how I got my bounds there. So then we'll multiply by 0.2, plus, now we're going to go to the next one, okay? We're going to read right in the middle of 1.2 and 1.4, so that is f of 1.3, and then we'll multiply that by 0.2, plus, okay, here's f of 1.5 times 0.2, and then here's f of 1.7 plus f of 1.7 times 0.2, and then finally we've got halfway here, and this plus f of 1.9 times 0.2. In this example, it didn't take very much for me to go out and find those midpoints, okay? And that's because it's pretty simple to figure out. If you have a bounds of 1.2, finding the midpoint, it's going to be at 0.1, all right? But what you want to get is that these values, they're just each one is halfway in between each one of your intervals. So if my interval is 0.2, okay, my first value is 1.1, my second one, 1.0, excuse me. My second one is 1.2. Then we're going to be looking for the midpoint between those two. Okay? So this ends up equaling, well, now I've got to go figure out what 1 over 1.1 is. All right? So one of the things that I'm going to do is I'm actually going to factor out 0.2 because everything is being multiplied by 0.2. So you can see you could factor all of that out. And then I'm going to end up with 1 over 1.1 plus 1 over 1.3 because that's the function. The function is 1 over x. So I'm going to plug in my value 1.1 into 1 over x plus, and then we have the third one will be 1.5 plus 1 over 1.7 plus 1 over 1.9. And that gives me every single value that I'm going to have in my integration. Okay? When I plug that all into my calculator, what I get is this ends up equaling 0.691907. Okay? Pretty straightforward, right? Basically what you're going to do is you're going to be calculating midpoints. All right? And so what we want to do, we're calculating midpoints between any two intervals. So we break up all of our equation into intervals, all right? And then one by one, we'll calculate the midpoints of each one of those intervals, all right? Then I will find the value of the function in each one of those intervals, add all of those up, and then multiply finally by the step size, by delta x. Now the approximation that we got for this, we got the integral of 1 to 2 of 1 over x dx ends up equaling 0.691907. Now, if I actually go out and integrate this, the integral from 1 to 2 of 1 over x dx is going to equal the natural log of x evaluated from 1 to 2, which ends up equaling 0.693147. Now, what we want to do is we're going to calculate something called the error. All right, so the error due to the midpoint rule, we'll call it E, is going to equal, it'll be 0.693147. That's the actual value from the integral minus 0.691907. That is the value that we got as our approximation. By the way, this is an approximation, hence I should make my curly cues. That's my approximation. When I do that subtraction, what I end up with getting is I get 0.00124. So what we can see is that this midpoint rule actually gives us a pretty good approximation. Turns out that from the standpoint of math-wise, it's not the greatest, but it's good enough for right now, and it certainly will allow us to demonstrate what it is that we're trying to demonstrate. Let's look at another example. Let's say, for example, I want to integrate from 3 to 4. All right, x squared dx using the midpoint rule. And we'll use a notation with M4, meaning that we're going to utilize 4 intervals here. So M4 being the midpoint rule, 4 being the number of intervals. So let's just kind of imagine what this looks like. We're going from 3 to 4. And you know what? This is not going to be a very good approximation. And the reason why it's not going to is because of the amount of space in between. Like if we start at 3, right? 3 starts at 9. Okay, in terms of y, and 4 goes up to 16. Okay, so there we go. It goes from 3 to 4, and that's 16. The fact of the matter is that as the slope gets steeper, the midpoint is actually going to end up giving us a worse and worse and worse approximation. Whereas with 1 over x, it wasn't so bad because between 1 and 2, we didn't have a huge difference in terms of the overall slopes. All right, but in this case, we're going to. But for the purposes of instruction, let's go out and let's kind of imagine a cross section where here's 3 and here's 4. Okay, and so we'll do one of these things, and there you go, scale, but it kind of looks something like this. Okay, now delta x is going to equal 4 minus 3, okay, divided by 4, which equals 1/4 or 0.25. So on my picture, on my drawing, I'm going to write each one as 0.25. So I got 3.25, and then I have 3.5, and then I have 3.75, and then finally 4. So now I'm going to imagine my values here. Now, here's the thing with 0.25, right? The picture looks the same, but the value here is a little bit different, right? It's going to end up being f of 3.125. All right. Same thing if I go up here to between 0.25 and 3.5. All right. So this value right here is 3.125. This is 3.375. This one right here is 3.625. And this value right here should end up being 3.875. Okay? So now using the midpoint rule, what I can do is I can just write this as delta x, right, times, and it'll be f of 3.125 plus f of 3.375 plus f of 3.625 plus f of 3.875. And what this will equal then is this is going to be 0.25 times, and this will be 3.125 squared, because our function is, remember, as x squared, plus 3.375 squared, plus 3.625 squared, plus 3.875 squared. So now pause the video for a second and go do your calculation. And so what I get when I do that is I get 12.328125. And that's my approximation. Okay? So what we'd say is that the integral from 3 to 4 of x squared dx is approximately equal to 12.328125. Now, the fact of the matter is that we don't actually have to do that. We do know how to actually integrate this. This is going to be from 3 to 4, x squared dx is going to end up equaling x cubed over 3, evaluated from 3 to 4. And this ends up equaling, or pretty close to equaling, 12.3333 repeating, okay? And so you notice now what we have is we have this error here. The error is going to end up equaling the actual value, 12.3333 repeating, minus 12.328125. And that's my error, right? The error is basically the difference between the actual value for the integral and the one that we found. And so what I get here is I get 0.0052, and then basically 1, all right, if we round. And that's my error. So still not a terrible approximation, pretty close. Now, in some cases, you're going to get close approximations. Other cases, you're not going to get very close, right? What we do know, a basic principle here is as I increase the number of intervals, I should get a better and better and better approximation. So a little bit later on inside of this video, we're going to talk about how do we find what the maximum error is given a particular step size. The next rule that we're going to look at now is the trapezoid rule. And so the trapezoid rule is just another way of determining the value or the area underneath the curve, okay? And so what we're going to do is we're going to imagine, again, I've got my curve, all right? So this is my curve. And what I'm going to do is I'm going to say, okay, well, let's imagine that I have, here's, this is going to be xi, and here will be xi plus 1. Okay, so there are those. And the best approximation would be if I created a trapezoid. Okay, like if I kind of imagine what I just did right there is I took my left-hand value and then my right-hand value, okay, and I constructed a trapezoid. That's it. All right, basically I kind of imagine that I drew a line here. Okay, I drew a line here that then gave me, kind of a better approximation. And I can kind of do that with each and every one of them, right? I've got this one here, there's that trapezoid, and then I have another one here, okay? There's another trapezoid, and you can kind of see that they actually end up approximating the curve even better than those midpoints do. So the midpoints end up being better on the whole than the left and the right hand sums, and the trapezoids end up being better than our midpoints. Well, the equation for a trapezoid is going to end up equaling, what we'll end up with is we're going to end up with the area equals 1/2, and it'll be base 1 plus base 2 divided by, or times the height, times h. Okay? And so what we want to do is we want to imagine that this is base 1, and this is base 2, and then my height is my delta x. Okay? So base 1 is going to be f of xi, right? The first value. Base 2 will be f of x, xi plus 1. All right? And so my area of any one trapezoid, okay, is going to equal 1/2, and this will be f of xi plus f of xi plus 1 times delta x. So if I were to rewrite all of that, that actually is that under the trapezoid rule, my area, okay, or my integral, okay, the integral of f of x dx, all right, from a to b will end up equaling the sum I equals 1 up to n of 1/2 f of xi, f of xi minus 1, actually, because we're going to start at 1, f of xi minus 1 plus f of xi, okay, times delta x. And delta x will end up equaling b minus a divided by n. So basically that's going to end up being our step size. All right. This f of xi minus 1 and f of xi, it's the same principle, right? It's just that if we generally going to start at x0 and x1, okay, rather than at x1 and x2. So that's why we use f of xi minus 1 and f of xi, right? So we can start our summations at 1 and start our summation at 1. All right. It's just a mathematical thing from the perspective of actually doing this calculation. It kind of works exactly the same way. So now let's actually use this. Let's use the trapezoid rule, and this time, and we're going to do it with n equals 5 to approximate. And let's do this approximation now again. Let's do the integral from 1 to 2 of 1 over x dx, just like we did before. Okay? And so what we'll do now is I'm going to actually figure out, okay, so if I'm going to write my equation, so this is going to be the sum I equals 1 up to n, and my delta x is going to end up equaling 2 minus 1 divided by 5, so it's going to end up equaling 0.2. So it'll end up being 0.2 times, okay, and this will be basically 1 over xi minus 1 plus 1 over xi. All right, and so that's going to end up equaling times 1/2. Excuse me. So this will end up equaling 1/2 times 0.2, and now we can do that summation. Okay, so this is going to end up equaling 1 over, and we'll start with 1 over 1, because that's the first value, plus 1 over 1.2. Okay, and that's my first grouping, plus, and now we've got 1 over 1.2 plus 1 over 1.4, and that's the second trapezoid, plus 1 over 1.4 plus 1 over 1.6 plus 1 over 1.6 plus 1 over 1.8 plus 1 over 1.8 plus 1 over 2. And that's my last trapezoid. Now what you should notice, or what I want you to notice, is I want you to notice that I have the 1 over 1.2, 1 over 1.4, 1 over 1.6, 1 over 1.8. They're all actually mentioned twice. The only ones that aren't are the first and the last ones. Okay, the first and the last values. And so if we went back up to our picture, you could see why. There's only one trapezoid that includes the first value, that includes x0. And there's only one trapezoid that includes xn. Okay, so it's just the last trapezoid that's going to end up including xn. So consequently, what that means for us is that we can actually get an alternate way of writing this particular equation. The alternate way is actually going to be, well, we'll take our 1/2, right? And this will be times delta x. And the way they write it is it's going to be f of x naught plus 2 times f of x1. So we'll multiply the first value, like in this case, 1.2, okay, plus 2 times f of x2. And we'll do this all the way down until we finally get to f of xn. So 2 of f of x of n minus 1, right? The one right before f of xn. And then finally f of xn, okay? And so this is one of those things that you can use in order to kind of like shortcut the amount of writing that you need to do. Okay, so now for us, that's going to give me 1/2 times 0.2. So this will end up being 0.1 times, and it'll be 1 over 1. So exactly 1 over 1 plus 2 times 1 over 1.2 plus 2 times 1 over 1.4 plus 2 times 1 over 1.6 plus 2 times 1 over 1.8 plus 2 times 1 over 2. Not 2, excuse me, just plus 1 over 2, because that's the last value. So when we go in and we calculate our value here, we end up with 0.695634921. So what we'll do now is we'll calculate our actual error. And if you remember, our error is the actual value for the integral. And this is 1 over x, so this is going to end up being the natural log of 2 minus the natural log of 1. Okay, and then we'll subtract from that the value for 0.695634921. Okay, so it's the actual minus the approximation, and we're going to put this in absolute values because error is always positive. Okay, so when we do that, we end up with 0.002487774. Okay, and so that's the value for, or that's the error value for our integral using the trapezoid rule. Now, one of the other things that we might want to do is we might want to find something called a relative error. And what the relative error is it's the error divided by the actual. Okay, so it's what percentage of the actual value are we off by. So in this case, it's going to be 0.002487774, and we'll divide that by the natural log of 2, right? Because that's what our actual value is. And we'll put that in absolute value as well, and that's going to end up giving me 0.003589, or 0.3589% of the actual value is accounted for by our error. So let's talk about how do we calculate the maximum error for the midpoint and trapezoid rule. So sometimes we're not actually able to calculate the exact value for the integral, and so we can't actually calculate what the exact error is, which is fine because we're going to use approximate integration when we can't actually calculate what the exact value is for the integral. So what we want to do is we want to actually be able to calculate what the maximum error is. So when we talk about maximum error, we're talking about what's the largest that the error can be given a particular number of intervals that I calculate and a particular function. So here's how we're going to go about calculating that error. So we're going to let f of x be a continuous variable over a to b, that's our interval, having the second derivative f double prime of x over the interval. So we're going to calculate f double prime of x, and when I show you the example, you'll see. If m is the maximum value of f double prime of x over a to b, then the upper bounds of the error using mn, which is the midpoint rule, and tn, the trapezoid rule, to estimate our integral are, for the midpoint rule, it'll be less than or equal to m. M is that max value of f double prime, times b minus a cubed, okay, that very clear, divided by 24n squared. And for the error in the trapezoid rule, Tn is going to be less than or equal to m times b minus a cubed over 12n squared. So what we'll see is that the maximum error for the midpoint rule is actually half of what the maximum error would be for the trapezoid rule. And so when we're actually doing approximation, what we probably will want to do is we want to look at the graph and make a determination as to which one is the best one to use to do our approximation. And that all depends upon how the graph actually looks. So let's look at an example. So here's the question about this example. What value of n should be used to guarantee that an estimate of the integral from 0 to 1 of e to the x squared dx is accurate to within 0.01 if we use the midpoint rule? So what we're going to do, we're going to utilize this one. We're using the midpoint rule, so we're going to use that first one. And what we need to do is we need to make sure that 0.01 is less than or equal to m times b minus a cubed over, okay, 24n squared. All right. And so our unknown, n, is going to be what we're solving for. We'll solve for n. B is going to be 1, right? So our interval is 0 to 1. So B will be 1, A is 0, okay? And m is going to be the thing that we're going to have to calculate. We're going to have to calculate m. So m, remember, is equal to basically the max of f double prime of x in absolute value. So we'll calculate f double prime of x. F double prime of x is going to equal e to the x squared double prime, which will equal, okay, and so we'll do one at a time. I'll end up with 2x e to the x squared, okay, prime, and that will then equal 2 e to the x squared plus 4x squared e to the x squared. Now, if you look at the graph here for this function, for e to the x squared, the graph of e to the x squared looks like this, right? It's basically just goes up really fast. I mean, like, it rises really, really quickly, but it's continuously increasing. It's always increasing. So its max is when x equals 1, right? Because it's a continuously increasing function, so its max is going to be when x equals 1. So we'll just plug that in. So f double prime of 1 in absolute value is going to end up equaling 2 times e to the 1 plus 4 times 1 times e to the 1, okay, which is 6e, all right? And so that's going to be our maximum value. So we found the second derivative, okay? We found the second derivative for our function, all right? And then we figured out graphically, or you might have to take the third derivative and actually go find where you have critical values. But we took the second derivative and we found, we looked at graphically and we found that it's going to be largest at e. You know, actually, now that I'm thinking about it, it's continuously increasing. But not only is it continuously increasing, its concavity is getting bigger and bigger and bigger because it's just kind of shooting upward. So that's actually a key point, because we want to know when the second derivative is the largest, okay? So you'll have to go out and probably do that graphically, or you might have to do that using calculus, okay? All right, so now we've got that m will equal 6e. So what I have now, I'm going to have 0.01 is less than or equal to 6e times 1 minus 0 cubed, all right, because b is 1, a is 0, times 24n squared. Okay, and now we'll end up with 0.24 n squared will have to be less than or equal to 6e. Okay, so n squared is going to be less than or equal to 6e over 24, 0.24, and that ends up equaling 8.2436. Now, because we want a minimum, all right, we want a min of 0.01, that's going to come when we have n equal to 8.24. N can't equal 8.24 because that doesn't make any sense. So we're actually going to need to round up. So we round up to n equal to 9. Okay, so we'll need at least 9 in order for us to get that error bounds of 0.01. Okay, and that's how we go about finding those maximum errors. All right, so what we've gone over here inside of this lesson is we've gone over the two different methods that we have in order to do some numerical approximation. We've got the midpoint rule and we've got the trapezoid rule, and then we've talked about error, right? Because what we're doing is finding approximations, so we should understand that error is going to happen, all right? If we want to find the maximum amount of error, here are our equations for the max amount of error given the particular step size and given a function, all right? So that concludes the lecture.